Welcome to the Computational Sustainability Virtual Seminar Series. Scheduled presentations through May are on the website at the center of the page. We are happy to offer this opportunity for those interested in computing and sustainability across the globe at both small and large institutions. This virtual seminar series is being organized by CompSusNet with support from the National Science Foundation and Cornell University. My name is Doug Fisher, and I'm the Director for Outreach, Education, Diversity, and Synthesis of CompSusNet. During the webinar, you can ask questions through the question and answer facility on Zoom, which will be relayed to the speaker as time allows. If you would like to ask the question yourself, you can just say so. You can also use the chat window for this. And again, you can simply give the question there or tell us that you would like to ask it and we'll queue you up. If you would like, find the chat window now and write hello to everybody who's online and say hello back. Today it's our pleasure to have Professor David Shmoys. He's Associate Director for CompSusNet, one of the Associate Directors. Professor Shmoys is also the Laibe Acheson Professor at Cornell University in the School of Operations Research and Information Engineering, and also in the Department of Computer Science at Cornell. He is currently the Director of the School for Operations Research and Information Engineering. His research focuses on design analysis of efficient algorithms for discrete optimization. He's the 2013 received as co-author, 2013 INFORMS Lanchester Prize, formerly Editor-in-Chief of SIAM Journal of Discrete Math and Research in Mathematical Sciences. And he is currently an Associate Editor rather, of Mathematics of Operations Research. So, David, it's a pleasure having you here today, and go on.
Great. Thanks, Doug. And thanks you all for joining remotely. I have to say this is the first time I've ever done something like this, so it's going to be a learning experience, and we'll hope that everything works the way I want it to. So I'm now going to try to share the screen. So I'm bringing up the talk.
Looks good.
And slideshow from start. Good. So I'm going to talk about ongoing work with a group of colleagues, PhD students, past and present, master students, past and present, and undergraduates, past and present, that have been all engaged in this work. And this is a broad collection of, this is joined in particular, mostly joined with Daniel Freund, the current student, Shane Henderson, a colleague in ORIE, and Eoin O'Mahony, who's now at Uber, having graduated to 4 wheels from 2, who finished his PhD, supported by the earlier expedition here at Cornell. And what I'm going to talk about is a range of models and algorithmic questions that are all in support of bike sharing systems. So for those of you who might not be familiar with what bike sharing is, the core of any bike sharing system is a map such as this, that's in front of a station that you see in the background. A station consists of docks and a set of bikes at any given station. And of course, the key element that presents all of the inventory challenges are the role of the user, who can rent a bike at any station and return it to any other station, thereby creating a sort of a two-sided inventory management problem for the common set of resources.
Is it an actor?
What? Yeah, that's DiCaprio.
Oh.
So if you use a bike sharing system, such as the one in New York, City Bike, you have access through an app to a map like this, which shows where there are stations and also shows the fill level of each station. So this station at the corner or let's say this corner of University Place in West is about half full. That's the dark blue showing that we know what the current status is. If I just focus on City Bike in New York for a moment, just to give you a sense, it started in May 2013 was its launch. By now, there are more than 1.5 million rides a month. Okay, for the riding season between March and November, the winter months when you have snowstorms like we had this week are clearly not the same thing. Total over both last 2 years, we've been over 10 million rides. Current status, when we go back to riding season, there will be more than 9,000 bikes on the road at any given time. There are almost 600 stations at this point, but even more interesting that there are still massive ongoing expansion of the system. And we've worked together with City Bike really from their inception, ranging from the first thing that we did in their first week was help schedule the station battery replacements to manage crises, but really the focus now is in what I'll be calling rebalancing. And just give you a sense of how the profile changes are over the last few years. The following graph depicts the growth just within the US of bike sharing usage, where you see by last year there were almost 30 million rides nationwide across a range of systems. Almost all of these, the ones that I'm highlighting, are actually run in concert by a company called Motivate, which owns all of these. And we've been working with many of those individual, those separate places, Vivi in Chicago and hopefully in Boston in particular. And one of the things that's going to shoot out of nowhere next year is a Bay Area bike share, which is currently small at about 700 bikes, will be 7,000 come July or August. So the main operational challenge in operating a bike sharing system is what I'll call imbalance. So on the one hand, on the station on the left, it's full. The rider showing up is, might be worrying when he's actually going to have a dock available. On the other hand, the person arriving at the station on the right, there are no bikes to do. So this is a endemic thing. And I thought I'd start by showing you a day in the life of the city. So I'm going to play a movie in which, just to sort of walk you through what you'll see. At the top, I'll tell you, you'll see the clock will start at midnight and we'll circle around till midnight at the end of the next day. Each of those little dots corresponds to one station. This was done in early summer last year, so the expansion was only midway through Central Park. To give you a sense of the current expansion, it's already at the north end of Central Park, and early spring it'll go up to 130th Street, just as this is really ongoing change. The diameter of each of those circles at each station represent the net change in bikes, and the color shading in red or blue will indicate whether it's outflow or inflow. Okay, so let me start the movie. This is always a thing that okay, there we go. Yeah, good. Okay, so it's, the clock is ticking. This is New York. It's the city that never sleeps. So that really there is still activity through the hours. But of course, as we head towards dawn, the city will awaken, and we'll see this first in terms of people renting at the transportation hubs around Penn Station, the Port Authority, and coming down to the financial district. Here you see the East Village, which is residential. You're having people run, and the Midtown Corridor, which is where people are going to bike, and the Upper East and West Side, which are more residential and going out. Now the rush hour is calming down. There's sort of not so much activity. It's still quite, it's a robust amount of stuff happening. We have a little bit of a pickup for Midtown lunch, and now we're going to start rolling into the afternoon, and we're going to see exactly the reverse of what we saw before, that we're going to see bikes coming out of the financial district, coming to the financial hubs, coming to the East Village, coming to the residential areas of the Upper East and West Side. And then the rush hour starts fading around 8, and it lasts a little bit even through 9. We've got a bit more activity, and then life gradually fades back, and we go back to black. That's fade back to where we started. So that gives you a sense of the way traffic works. In the city, it's largely what you might think of sort of anti-symmetric flows between the morning rush we had. It's not exact mirror image. If a ride here was always complemented by a ride there, a lot of the imbalance issues wouldn't be the same. And it's also complicated by the fact that you have all this during the day traffic that's further changing the state, and a variety of issues. So that's what I want. So one of the good things about managing a system like bike sharing is that we actually know the state of the system at any given moment in time. And we can look at the data. So for example, this is a station in Brooklyn, Atlantic and Fort Greene Place. And this is one day, and just so you're going to see a lot of plots like this, so that you see what I'm doing. That green line across the top represents the capacity of the station, how many docks there are. So this is a station with, I think, 62 docks. The blue line represents the fill level at any given point in time. So we start out with maybe 3 bikes, we go down to 0 at this point. This sort of sudden increase, I mean, I don't know this for sure, but this looks exactly like a truck delivering a bunch of bikes, doing some occasional amount of midday rebalancing. Maybe they really should have done it earlier, as you sort of see that there was outage. And then you have sort of stable plots throughout the day. And you might say, well, is this sort of a typical day? And the answer is, yeah, if we do two other days the same week. Here, actually, we started with better base levels, and we had less outage time. Here we had no outage time in terms of that. But of course, one of the takeaways from this picture is that this capacity is absurd. There's no reason we needed to have allocated this many docks to this station.
And weekends are a different pattern.
Weekends are different.
Pattern.
Weekends are a different pattern. And then you're going to see my incoming email messages. What can I do?
You can stop Wi-Fi.
That's up now. No, we can't because of.
Oh no, you can't. You can't. How smart.
Okay. So that was a pretty calm station, but let's look at a station in Midtown, 52nd and 5th Avenue, and you see. I mean, this is a smaller station. Kind of strange, indeed, rather not well designed. It's only 40 docks, but you see much more rapid swings and really going almost all the way up to capacity and completely depleted. And to look at these things, so if you think about the movie we saw, Midtown is a place where you have an infusion of bikes in the morning, and you have a depletion in the afternoon, by and large. So this depletion here is a rebalancing truck. This is emptying some bikes from this station, allowing the possibility of people actually using it to actually deposit bikes. And similarly, this is again a couple of trucks taking away bikes, in the middle of the rush hour. There are only a small number of stations that can be targeted by trucks that can only deal with it, and there are sort of certain, in terms of the guarantees that are required that City Bike has with the City of New York of why certain stations are targeted. But nonetheless, this is an effective rebalancing. The flip side, and you really sort of see the dramatic use. These peaks are all, we brought in some trucks and they rapidly got taken out from there. So
good timing.
And you see that, I mean, this is again, not an unusual day. You look at the week and it's very much the same sort of patterns. Okay. So again, you really have a sense that you know the data that's there. Of course, you have to be a little careful of how well you think you know the data. If you look at this station in the Village, or Lafayette and East 8th Street, I mean, we've said that the capacity is at this green line, but if you look at this random walk that's occurring here, there's no way that it's just arbitrarily stopping one short of the capacity. What's happening is there's a broken dock at this station, because if you were thinking about it, it's going up, it's going down, it's going up, you would have expected to hit that capacity line if all the docks were actually working. And so because we see the data missing that capacity line, we know that actually we don't have this many docks that are functional with one fewer dock. There's some amount of sort of cleaning the data that takes place to sort of really know what true functionality is. Okay. Of course, the data that we know are based on trips that actually did occur. But one problem that's true in all kinds of inventory things, and this is true for the traditional news vendor problem, is that you don't know about the things that weren't bought because there wasn't inventory in order to buy them. And so there's this notion of censoring of data. And so we don't know the times that people didn't ride there if we're trying to sort of measure latent demand.
So beyond the capacity you have.
Yes. So one thing we can do is use the fact that of the stochasticity, both in terms of when we rebalance and just the nature of the system, to actually get a better handle on inferring what the true latent demand is. And a graph like this is useful. So let me walk you through what this graph shows. So this is a month worth of weekdays. at a relatively busy station, pretty early in the lifetime of the system. And we're color coding each 10-minute interval by how many bikes are at that station. Only really paying attention to, are we almost out of bikes? Are we almost out of docks? Are we basically okay? Okay, so green is okay. Red is hot in terms of, we're running out of docks, and blue is cold in terms of we're really nearly running out of bikes. And if you look at any given time slice, then there are a lot of times, for example, at this time, where we're out of bikes entirely. And so we can understand the latent demand by looking at the rate of usage just conditioned on the fact that we actually have bikes. And so by doing this deconditioning, we're able to get a better estimate on the flow of bikes. And in general, one of the things that we use as a tool is a simulation model for the system. And one of the great things about a system like this is we have tremendous access to all sorts of data. So one thing that you want to do in building a simulation model is you'd like to sort of know if a person rents a bike at Penn Station and returns it on the Upper East Side, how long is that bike typically out for? So it's really out of service. And so if we just think about every pair of bikes and we think about plotting as a scatter plot, this is on a log-log scale. The distance between the pairs of endpoints and the duration that bike is out for, you actually see that you have a pretty good fit that's there. But actually, if that was 1 day's worth of data, if you put 1 month, all of a sudden you can see even more in the data. What do you see? Well, there are a couple anomalies. If you see that there are a few distances which have anomalous behavior. And actually, if you drill back on, the people who so first of all, it's anomalous with respect to sort of a horizontal line there. Sort of seems like it's sort of a big threshold. What is that horizontal line? The way the structure works is that an annual subscriber can rent a bike for up to 45 minutes without incurring overage charges. That's the 45-minute time point. And so that people are really sensitive to making sure that they have their bikes back, and then you have much less usage above that. But there are exceptions, and those exceptions actually tend to get focused on distances that happen to be between common tourist pairs. So between the east side and the west side of Central Park, for example. So one of the things that this is all working towards is we want to sort of help plan the operations of the system through the data that we're observing. And sort of the highlights that I've sort of tried to get is that most of the trips are actually in the commute times between 6 and 8 a.m. in the morning and 4 and 8 p.m. in the evening. We can sort of think of a planning period largely as being from 6 a.m. to, let's say, midnight. And then we have a more quiescent time between midnight and 6 p.m. that we can send the box trucks out in force and try to readjust where the bikes are so that we can start the day with the bikes where we think we want them to be in. But one of the things that is sort of one of the fundamental messages of all the work that we've been doing is that we want some sort of metric to evaluate both what the current state is as we evolve, as the system evolves during the time, and just how we're doing overall in performance. And the metric that we're going to focus on is with respect to a given stochastic model of demand, that we're going to focus on the expected number of eventually stockouts of either side. And we have these two-sided kinds of stockouts, either that there are no bikes available or there are no dock available. You can sort of view that as the expected number of upset customers along the way. And I guess I know that asking questions is tricky, but don't hesitate to send along questions, and we can filter them back to me, and I'm happy to take calls and get questions. And so the tools that I've talked about are actually implemented today. So that in terms of how New York City manages its operations is all guided by the metric that we're talking about and many of the algorithmics underneath it. And I'll drill down more there. So first of all, I need some way of thinking about what is the demand pattern. We saw the movie and we saw that. And the first thing that we're going to start with is we're going to make an assumption. And there are aspects to the assumption which need care and examination, is that we're just going to assume in effect a Poisson flow of bikes. And I'll say this a little bit more, and that's the rates of those Poisson flows are going to be determined exactly in sort of this decensoring way that I talked about from data. So we're going to have a data-driven model there. we're going to think about modeling each station as a continuous time Markov chain. And again, what we're going to be interested in is computing the number of upset people. Initially, our plan was to think about it's restricted to rush hour, but now we're really going over a 18-hour planning period. Over a rush hour, I want you to think about the model of a station, as I said, a continuous time Markov chain, where the state of the system is the number of bikes in it, and the number of different states is the number of docks plus one. It can either be empty up to capacity, and let's say we have a constant, we're thinking over a rush hour, where we'll for the moment assume that we have a constant rate at which people arrive at that station lambda to rent a bike, and a constant rate mu at which people arrive at that station to return that. And then as a function of the initial state I, so if how many bikes are in the station at the start of the planning period, what's the overall cost in terms of the expected total number of outages? And that's an expression that captures it, and just sort of walk you through it. So we were taking an expectation with respect to the flow rate out. We're going to integrate up to the given moment in time. And we're going to be thinking about the indicator variable is that empty, conditioned on the fact that at time zero it was with I bikes. And this gives us, oops, go backwards. This gives us an initial way of thinking about a cost function. If I have I bikes at the start of my planning period, how much is it going to cost me over that planning period in terms of my objective function? Now, this turned out to be bad modeling. That I said that I was thinking about a constant rate of rentals across the morning rush hour, and it always goes back to looking at data. So look at this station and ask the question of, if you look at the morning over the planning period from 6 to 10, is that constant rate? And the answer is no. I mean, on the days that there's really business, we have this complete train, fills in and turns around suddenly a little bit after 8 o'clock. Just complete reversal of the behavior. So, and I've been planning, the model that I talked about planned across that it would be constant throughout that period. And now the answer that this is a little bit of an anomalous station, in that this is outside Bellevue Hospital, and that's actually near a daycare center. And so both contribute to the fact that that people in the neighborhood rent a bike to bring both the child to daycare and arriving staff. And then the staff change occurs at the hospital at 8 a.m. And then all of a sudden there's this complete changeover, in fact, largely driven by the hospital. So we need a little bit more sophisticated model, and a very natural thing is, let's just assume we have piecewise constant Poisson rates. What we do, in fact, is sort of getting our hands dirty. We currently do things in half-hour intervals, and so that means there are 36 planning intervals over one day. But now we do exactly the same sort of model, just with this additional generalization. But again, by and large, the cost function is exactly the same. And just the notation is so important that we're now going to be having states that go from 0 up to the total number of empty docks and number of bikes. D sub I is going to be the number of empty docks we're allocating at a given station, and D sub I is the number of bikes, full docks with the bikes that are there. And then we're going to have some cost function condition on the fact that we start with that many bikes. Okay. One nice thing is that the machinery that we had to compute our metric for constant rate Poisson processes just naturally expenses through a nice recursion. So if I want to think about the cost incurred from periods k to the end of the planning period, well, that's the cost incurred in the kth period, plus the expectation is linear, plus the cost from here on out. So what we just need to know is if I'm in a given state here, what's the probability that I'm in a given state there? And I can just build a nice recursion that says that the cost backing up one planning period is the cost in the next one, plus a probabilistic weighting of what happens from here on out. And that's an easy calculation to do. And so although the problem scales and we are starting to feel the effect of a larger scale problem, nonetheless, we can get our hands on computing this objective function. If I tell you for a given set of Poisson rates, what the starting allocation is for empty docs and full docs, I can compute the expected cost. So I thought just to give you a few sense of what these cost curves look like. So here's a station outside the Port Authority. And what we're looking at, these are costs over the 18-hour planning period for the number as a function of this is a station that has between 0 and has a capacity of 45 docks, and now we're just allocating a number of bikes, and we just can see that the more bikes that I have at 6 a.m. the better. That's just purely, just absolutely a linear improvement in terms of, and that of course goes back to the original thing that we saw, that was one of the first places to wake up in terms of transportation hubs of people wanting to rent bikes. That station, that Dull station in Brooklyn, Atlantic and Green, indeed, it's not so sensitive in terms of if I have anywhere between 20 and 40 bikes, I'm not expected to have any outages. Though if I start at 0, I may expect to have a couple outages. So, on the other hand, Midtown, again, we want to start that basically empty because we know that the bikes are coming. And then you get a range of different behaviors over stations. And of course, as I think about what the goal is, then you want to be able to achieve the minimum. And so that gives rise then that we can think about a mathematical programming formulation. I have a fleet of bikes. I have a total amount of size, and I get to allocate those bikes across the city at 6 a.m. And I want to minimize the total number of upset customers. What's the way to do this? And I have their theorem to prove in the shape of all the cost functions I had were indicative that these are convex, that this is a convex objective function. So I have a convex program to solve. And in fact, I linearize because I really am only interested in the integer points. I can linearize this and solve a linear version. And this, as a linear program, is a structured enough linear program that it has an integer optimum. So I just go ahead and solve this formulation, and I can quickly then determine the optimal number of bikes to allocate to each station between 0 and its capacity, given that I have a fleet size of V bikes. Okay.
So what is about the structure makes it as an integer solution?
It's that it's really only one knapsack constraint. It's very, I mean, it's essentially that it's sort of a unary knapsack kind of problem. We have, if in a knapsack we had coefficients on that, then all of a sudden the last variable might be the fact that this is just
yeah, I see. Mm-hmm. And it's not that difficult.
So unfortunately, life is not so simple. So I just said that we can compute the optimum for how many bikes should be where at 6 a.m. So this is a shot again from last summer at midnight, and I'm color coding each station to give you a sense of whether there's work to be done. White means I'm close to the 6 a.m. optimum of what I really want to be true, and red is when it's far. So that's the snapshot of the picture at midnight. And now what happens by 6 a.m.? And you look at those pictures and you think, oh, gee, not much. Did actually anything happen? Yeah, a little bit happened. So there are a small number of stations. This one went from red to something white. And but so if I look at the current amount of allocation of resources the city is using to do that rebalancing, although they know what the metrics and they know what we're guiding them towards, they're actually not really moving nearly enough bikes in order to come to that. So, and this I've been hinting at all along because I knew where I was going. One of the things that was true is the system was set up without any knowledge of what the actual demand was going to be. There were gut feelings as to where there might be demand and where there might not be demand. But there certainly wasn't data, and now we have data. We have years of data for the initial footprint. And I mean, there were also political considerations that Brooklyn has far more docks than it needs because Brooklyn wants to be an equal partner to Manhattan, even though it doesn't have equal traffic. But one can still ask the question of, can we compute a better allocation of docks? I mean, in fact, the way these docks work is that they're really just heavy pieces of machinery that sit on top of the pavement. There's no infrastructure there. I mean, one of the ironies of the system is that in New York, the docks just are powered by solar panels and batteries. In contrast, in Tel Aviv, they're actually drilled down into the grid rather than on solar powered. Go figure. But they come in little modules of 2 and 3 docks each, and so there's a great deal of flexibility. And yeah, it's not an easy thing to do. It's it takes a crane and a flatbed truck in order to lift up a couple modules and then move them to some other station, but they can be completely reconfigured. So the question is, can we, what would be the advantage of computing a better allocation of docks so as to help overall manage the system?
Instead of bytes.
And if I go back to this model, you see that really I'm sort of almost in business. I mean, what would I need to do? I mean, well, I need that this upper bound all of a sudden becomes a variable rather than a constant input. And I'll need some allocation constraint on the total number of docks in the system, much in the way that I have a allocation constraint on the total number of bytes. So indeed, I can write a convex program this way, and I've opted to change variables that for each station, I'm saying, as I think about an initial configuration, I have this many of empty docks and this many of bytes filling docks there. So in total, I allocate that I have constraints on the total number of docks and the total number of bytes. Okay? So that's a convex program. And indeed, in the first of the work with Eoin and Shane, this is one of the things that we advocated. But already at this point, life became a bit harder. And one of the things that was the case is that I don't know how to prove an integrality theorem for this formulation. And in fact, if I sort of generalize the notion of what the cost function is, if I say that the flows are in Poisson, but I can give a somewhat worse distribution underlying what the demand distribution looks like, I can actually generate instances which it isn't integer. Now, of course, what does any good math programmer do? You solve it anyway, and you hope that it is. And the answer is, yeah, it's usually integer anyway. In fact, for all of the real inputs that we have, we don't know. So it's still conceivable that for Poisson flows, there could be an integrality. But this gives rise to a nice, interesting computational problem, which is called the dock allocation problem, that I have a piecewise constant set of demand rates, lambda and u, over each station in time interval. My performance metric is the total allocation, and I want to determine the optimal capacities. And this is the convex program. One other aspect is that the problem is little by little getting larger. That both in terms of the number of stations, the total number of docks in the system.
So how many variables? How big is this problem?
So the main thing are the number of cost curves that I have to compute in terms of, as I think about potentially, how many different allocations there are. There's something like 1.7 million cost curves that need to be computed if I were to do it in sort of an explicit math program. It's still handleable, but we're reaching the limit. But it turns out that this problem is much more well structured. And
nice.
And one of the things that often goes hand in hand with convex minimization or concave maximization problems is some sort of notion in a single variable or a set system. We think of some modularity. We're going to have an analogous set of diminishing marginal return kind of structure that we can prove here. And that's going to drive more sophisticated algorithms, that will be actually much more efficient and be able to solve the problem optimally. So I'm going to think about this notion of multi-modularity in the following way. So here again, the graph, this axis represents the number of full docs, this axis represents the number of empty docs. And what do I mean by a two-variable function being multi-modular? And this is a notion introduced by Hayek quite a while ago. Is again sort of diminishing marginal returns in a number of respects. So let me just sort of walk you through it in this color-coded way. If I look at this solid blue and this dotted blue line, what it essentially says that if I look at the right-hand side here, this is the advantage with respect to costs. So how much cheaper does it get by adding one more empty dock, keeping the number of bikes fixed, relative to doing it one larger. And what we're saying is that the most added benefit for the added benefit for one extra dock diminishes as a function of the number of docks that I have to start. So I have this diminishing marginal returns this way. The purple is analogous this way, that if I think about the marginal benefit of increasing the number of full docks by one, that also diminishes as I have more empty docks to go with it. And then somehow the more, maybe least intuitive is if I think about diagonals, that the diagonal line corresponds to the total number of docks being constant, because that's the sum of full docks and empty docks. And again, we have a diminishing marginal returns. And then there's a duality with respect to these two variables, that we have the same inequalities that if I reverse the role of empty bikes and docks. But one can prove that all these inequalities hold, and then we can prove that if I give you any realization of arrival, sort of a sample path analysis, that the cost functions are multi-modular. And this can be proved by a delicate induction argument, but nonetheless, we have that. And now we just have a black box of this multi-modular function for which we can then think about what that means to solve the resulting convex optimization problem. And what this gives us are sort of two really nice structural results in the following sense, that we can define a neighborhood structure on solutions. So if I think about a small perturbation as I think about the allocation over the whole system, here are some natural things that I could change. I could think about an empty dock, and I could move it from station A to station B. That's one way that I could change it. Or I could take a full dock, and I could say, move both that bike and that dock from station A to B. Or I could just move a bike from station A to an empty dock at station B. But then there are a couple more complicated moves that we can take a bike that's at one station and an empty dock that's at another, and move it to a third station where we're going to have that as a full dock. Notice that you can't build that out of these separately. And then we can sort of have the unwinding that. We can take a full dock at one station and decouple it, put the bike here and the empty dock there. So this gives us a neighborhood structure of moving around the space of all solutions.
So those are the valid moves.
So those are valid moves.
And do you cover everything with that?
Yes.
You are guaranteed to cover.
Because I can step by step move everything. And the somewhat surprising thing is that multi-modularity alone is enough to prove that an allocation is optimal. So bike and dock is optimal if and only if none of those local moves yields an improvement. So it's sort of like the simplex method in the sense that a local optimum is global. Now, in some sense, that becomes maybe a little less surprising with the next piece. Is in fact, you can even do so. One natural thing is I could just simply look for local improvements until I'm done. And that's good for warm starts and sort of doing some amount of change. But also that we can also show that I won't go through the details because I want to get to a number of other things, but that a very natural greedy algorithm, not quite the first cut of the greedy algorithm, can also be shown to be optimal. And it's optimal in the following saying that built into, and it's sort of a greedy augmentation that you can say that if I want to just move k docks from a current augmentation, that after k iterations, the algorithm actually finds the best improvement that you can if you're only moving k docks. So this gives us an amazing, really useful tool for the city currently, because it has this currently really bad allocation. and this is literally happening over this quiet period, that they want to know, we're willing to move, now unfortunately not many, 50 docs. What should we do? And now implicit in this result is that we can actually say, what's the best effect on the system?
So then this problem is not hard.
No, it's not hard, exactly. Yeah, so in spite of the fact I don't know an integrality theorem, it's not hard.
Oh, this is,
Yeah.
I think, interesting.
And in particular,
Yeah, so I guess the analogy with the LP. Yeah, I mean in LP, you don't necessarily have integrality all over. Yeah.
I mean, in some sense, if you think about non-bipartite matching, if you write the simplest formulation, that doesn't have an integrality theorem. There's just a better formulation which does. So that may be what's missing here, for example.
Yeah. Ah, this is quite interesting.
So another question that we sort of took a step back from and said, well, suppose this whole idea of rebalancing overnight is a bad idea. Let's just, let's think about, I mean, we've got this evolution of a system. I mean, underlying it, we can sort of think about some Markov chain that will eventually converge to some steady state. What's the, that gives us some senses of, suppose we're only worried about the limiting, behavior of this system. And let's just try to, instead of optimizing for the best thing to do with respect to perfectly moving everything between midnight and 6 a.m. back, let's optimize for what is the best thing in terms of what that steady state behavior looks like. And so we've done that for New York City. And so we can compare 3 different allocations. We can allocate according to the optimal allocation, assuming, for 6 a.m. to midnight, and then we'd assume that somehow or other we have enough truck capacity to between midnight and 6 a.m. move everything back to where it should be, which we know probably isn't going to happen, but even with this lesser amount, and we can think about what the cost is there. Or we can optimize for what we see we're really not affecting things. We can optimize how should we put the docs for this limiting behavior, and that's what we do there. Or we can think about the allocation that currently is in place. And look at what happens. And then we can think about sort of if we don't do any rebalancing on those, and we can think about if we actually still do the optimal amount, and we really do leverage the amount of trucks of how much improvement we can get. So, I mean, in effect, this is what's happening currently. This is the allocation, and we're effectively doing no rebalancing. If I, optimize for that, I get about a 30% gap between the cost of what my current doc allocation is and the optimize for that. If I optimize for assuming I could do the overall rebalancing, then I actually only degrade a tiny bit. So these 2 allocations are not so different, both in terms of the quality of the solution and in terms of the actual allocation. And similarly, I can think about, well, at the other extreme, even if I took the current allocation and I was able to do the optimal rebalancing overnight, which we saw we're not doing anything close to that, it's still way worse than either of the other 2 allocations. So we really see very directly how bad the current allocation is, and that either of these views of thinking about the steady state and not rebalancing, or doing the
what's the units there?
This is in terms of the expected number of customers who show up at either a station with no bikes within an 18-hour plan.
Okay.
So expected 20,000 people?
Yeah.
That are not going to be happy.
Wow. Yes.
That are not going to be happy.
They're not going to be happy. Yeah, indeed.
It's great.
So I mean, it's there. One of the underlying messages is that the system is undercapacitated. Pure. I mean, there's a crying demand for expanding the system, and essentially they're going as fast as they can. And yet, one of the other interesting things that came out of this is that even though we weren't worrying about how much we had to move overnight in terms of this optimal rebalancing, the two other allocations are also cheaper to rebalance than the current allocation. Okay, so
Have you looked at the number of customers that leave the system? And
yeah, we are. Yeah, and actually, then yes, these are all interesting. Yes, so these. So this was all in terms of the design of the initial system, and then there are sort of the operational things that one can do to improve and mitigate sort of the damage that the current system design or any system design at this capacity is going to. And I'm going to just briefly touch on a few additional topics and give you a sense of the kinds of work. And then the meta message is that this underlying metric of thinking about, for the rest of the planning period, how many expected customers do I have that are going to face a stock outage, is going to guide how we think about what kinds of actions should take place. So within rush hour, although there's some limited number of trucks that get used, one of the most effective things of rebalancing get done by these trikes. So this is a bicycle that's outfitted with a trailer, and on the back of that you can load onto that some number of city bikes. This one I think holds 5, and that you can then shuttle this trailer between one station which has too many bikes and one which has too few, back and forth through the rush hour to sort of try to get some amount of load shifted around. And a natural question, so there are ones that hold up to 12, we're going to do this during rush hours, but of course we only want this for stations that are relatively close to each other. And what we want to do is we want to figure out what pairs of stations should we be allocating the trikes to do. And again, we can use the same kind of continuous time Markov chain modeling. We will still want to most effectively use our trikes to do that. It involves sort of taking a pair of stations and coupling the continuous time Markov chain between the two stations, and then we're going to think about the shuttling back and forth effect. And again, we're going to still compute the expected number of angry customers, and we're going to think about, for every pair that's close enough, how much does that improve that station? So what we're in effect of doing is creating a bipartite graph of where the weights of the edges are actually even, doesn't even have to be bipartite, but in effect it does, because there are some stations that clearly have too many bikes and some that clearly have too few bikes, and that gives us the natural bipartition. And for each edge, we're going to essentially give it a weight that's the improvements of the objective function if I send the trike back and forth throughout the rush hour. And so in the end, I end up with a maximum weight k-edge matching problem in this bipartite graph. And so we can solve it and then allocate the trikes in that way. So that's one flavor of one way in which we can sort of use the metric. Mm-hmm. Same sort of thing happens with overnight rebalancing. Overnight rebalancing is largely driven by these box trucks. They have between 4 and 6 trucks that are available on a given night. In fact, very few, or about half of them, get allocated to a different issue overnight, in that another of the operational problems is that bikes break. And so what happens is that there are effectively red lights that are put on each station. And so overnight there has to be this traversal to gradually just pick up, some truck gets sent to this neighborhood and picks up all the broken bikes and then brings them back to the warehouse in Sunset Park in Brooklyn. But in reverse, every night begins in sort of helping to solve rebalancing with the set of bikes that finish their repairs in Sunset Park, and that they can help use to sort of ingest new bikes into the depleted stations. So the goal here is we have from 11 a.m. to 6 p.m. We have those 7 hours, and what we want to do is improve the state of the system with respect to the metric as much as possible. Mm-hmm. And we used a combination of an integer programming and a heuristic hybrid. One of the challenges is the data of the state of the system is only available 30 minutes in advance, because we see that the city only quiets down around 10 o'clock, and the last thing we want to do is be moving bikes when we really won't need them. So we need to wait. We need to wait. So one of the natural things we do is that we sort of compute the schedule in fragments, that we sort of compute an initial piece so as to get the trucks based on an estimate of where we think the demand is, and then after 30 minutes, we augment those initial paths for there. And again, of course, the goal is to optimize the state improvement. We've run a pilot on half a dozen nights or 2 weeks worth of nights. And in fact, this in terms of the metric, yeah, it's not in the 20,000 kind of level, but we get a good 20-30% improvement over what they're getting for rebalancing by their ad hoc methods. And you get this is sort of the kind of solution that evolves. Another thing, and probably one of the things that was most useful in making the system more resilient to demand, is a very clever idea that they had in effect giving surge capacity to stations. So think about the financial district. It's empty at 6 a.m. You've gotten the bikes all out of there. They're there, but the traffic is about to come. The traders are about to start coming to Wall Street on their city bikes from their East Village apartments. By 7:30, they're full. Now, you could have a box truck, this is what they did initially, had a box truck pre-positioned in the financial district. So at 7:30, they could just load it up and then take it, move the truck away. But now think about the reverse commute. Come 4:30 and those traders are going home, we're going to need all those bikes back. So why are you spending all this effort to sort of truck them, a large number of bikes, there isn't the same usage in the middle of the day. Let's figure out some way of storing more temporarily. So what they do is, and you sort of see a picture there, is they sort of basically stack the bikes on top of each other. Then although you might have a capacity 60 station, keep 6 docks alive as normal docks and keep them empty so that people can keep returning new bikes and taking bikes out for the people who do want to take bikes out. But for the other 54 docks, there's space between every pair of docks to stack in an extra 3 bikes and lock them down with hopefully sufficiently uncuttable cords.
So they are not really usable.
So they're not usable, but basically that
it's a storage. You just created storage to the system. Yeah.
But again, now it takes a person who's dealing with taking the bikes, that are as they come in, and then restocking them and locking them down. And so, how much they're willing to, use personnel to do this? Though they had, some budget for, I think it was in this case, was 6 corrals at that stage that they wanted to position. How again do you want to do that? And again, you can set up a natural integer programming formulation, a simple facility location kind of model, and here's sort of, this was the model that we advocated for 16. This was a not quite as effective model that we allocated for 15. Even if you did something that was purely locational, that was based on just outage minutes, and this is a purely locational one. And then we ran simulations so as to sort of see the range of effects that our corrals can have. And the takeaway is unquestionably that this is a much better method for allocating corrals. No, I'm not going to one of the things that drives many of the problems that this system has is the stupidity in the pricing scheme. So what got negotiated with the City of New York is that there are a limited number of options. You get $12 for a day pass, $24 for a 3-day pass, or you spend $155 for an annual subscription.
Mm-hmm.
Now, parents of a good friend of my daughter's who are avid cyclists in New York and have their own bikes say they spend well more than $150 just on maintenance alone for the bikes, let alone the fixed cost of actually owning it, never counting whether they actually have a place to store the bike, not counting the fact that requires that you have sort of cyclic cycling patterns rather than you can just use it for one rate patterns as your needs and rates. So this is priced way too low. Mm-hmm. And another thing is that a large fraction of the service is done by users who make more than 100 trips per year. So that's $1.55, even if it was just taking 100, in a city where it costs $2.75 to take the subway. So in terms of cost this is there. So one thing that we've been trying to do is sort of inject an alternative currency into the system, so as to sort of have more point-to-point prices and sort of insert incentives for users to make good rides as opposed to bad rides. And this seemed to be effective. And indeed, this is engendered, for any kind of ride-sharing work. And I don't have time, since I'm almost out of time, to talk about it in detail, but Sid Banerjee and OR and Daniel Freund, my student, and Doris Lucuris, Ava's students, have worked on a really nice queuing-based model to show approximation algorithm results that are quite strong for exactly how to set point-to-point prices when you in a queuing demand-driven model like we have here.
Mhm.
And one of the joys of working on this is that problems crop up where you least expect it, and the data is there, and you can do interesting things. So one of the things that we actually started with was this sort of sense of that you have to replace the batteries that are powering these stations. And if you look at the data, these are voltage levels of the batteries in stations across a handful of stations. And what you can delineate is sort of where they actually had to replace the batteries because it was no longer sustaining the voltage and had to be taken back to the warehouse and recharged. So this gives rise to an interesting stochastic optimization problem in terms of how do you effectively manage this replacement problem.
Mhm.
You might see that like this station actually practically needs no replacement. Ironically, that's its battery park because that faces south and it has no buildings blocking it, and so it's just all the solar panels actually do work.
Mhm.
But again, the sort of range of problems that come into play is really fantastic. There are a lot of ongoing things. One of the interesting questions of, okay, I have a particular allocation for the docks. We're using a given fleet size, but what's the right size? And it's a delicate thing, right? If I have too many bikes, then I'm going to have dock outages. If I have too few bikes, I'm going to have bike outages. And then sort of understanding, we're using a simulation optimization approach for doing that. This question of battery changes that I've talked about. There are interesting questions of detecting broken equipment, and in general, the data-driven analytic questions that come into play are really quite far-reaching. And then there are sort of even harder questions of, it's one thing to think about bike sharing in isolation and to think about these demands as being exogenous, but really, you have a multimodal way of people traveling, of a mixture of commuter rail and how do we actually help planning across? Suppose we could think about planning not just on the bike side, but on the other public transportation aspects, and how do we build models to actually think about that? And that's some of the questions that we tend to think about. Thank you.
Are there questions? Should we go to Doug? How is that?
You want to stop screen sharing?
Sure.
I can see it.
Nice picture.
So any questions from anyone, you can ask them on chat. Or if you're part of a live audience, you can ask them live. Yes, Warren.
David,
Yes.
so I love the mixture of stochastics and deterministic, okay? And I understand that you've also have worked in the area of doing sort of stochastic gradients to learn functions. I don't know if that came up in this talk, but I think you've given other talks that show that.
Mm-hmm.
I couldn't help but feel that in your deterministic optimization problem, you were optimizing a cost function that might have to be learned. Is that something that you've poked at?
I haven't poked at it, but I agree that's certainly a natural thing to do. In some sense, I don't feel there's too much bang for buck that's likely there, because I mean it's learning over time. I mean the dynamics of the system. Yeah, I don't know what happened to me. Oh well. I guess, are you seeing a blank screen? I think I'm seeing a blank. Do you see me? You don't see me. I don't know if my image got lost. Anyway, I'll keep going without the visuals.
What do they
I mean,
see?
so I see a blank screen of myself, just all black.
Yeah, that's what we see too.
Anyway, so
So I mean, part of the
now
Because the problem is that if it's learning over time, that's an important thing. Because the dynamics of how the system today, if I think about how that worked on any day that, as I think about re-simulating what the cost function might have been based on snapshots within a given month, that doesn't change so much. It changes a lot whether it's based on weather. I mean, if I think about ways in which the model fails, understanding the role of weather and forecast for weather.
Well, that was going to be my next question, because I would assume that, at the end of every day, you've got a forecast for tomorrow.
Yes.
It seems like it's an interesting problem to.
That is certainly very high on our list in terms of incorporating that into the model of having some good way to do that. But it's also the fact, at least in New York, and I think for all of these in the growth charts that I showed you, show that the problem that we're facing is that the usage patterns and levels are changing so dramatically on a month-by-month basis that if I spend too much time in building into learning, I may be learning yesterday's patterns rather than.
Well, but if you're doing the learning properly, it has to learn recognizing that it's a non-stationary system. Okay, so that
Correct.
has to be part of your learning model.
Absolutely. Yes.
Anyway,
But it's certainly an interesting range of questions to think about.
so here's a twist. So let me make your problem a little bit simpler,
Okay.
where maybe you have a discrete allocation, and you know what? Give me a list of 20 allocations, and I have to pick which of the best list of 20 allocations we have to learn. Okay, so that I'm going to take away your big integer program and just say, look, here's a list of 20 allocations of bikes. Pick which of the 20 that you want. Okay, you're going to use your integer program, but let me just do this just to simplify the illustration and make the linkage. So as we learn, first of all, that's a form of bandit problem, because you have to accumulate the rewards as you go. That puts it in the bandit class. Obviously, you've got something more interesting than a discrete set of list of 20. So that's
bandits with essentially infinite arms. They're interesting results out there as well.
Oh, okay, I'd be curious if there's computationally interesting results. But anyway,
Bobby Kleinberg, actually going back to his work at Akamai, has computationally interesting work on that. So
okay, well, so there's a number of communities who use this word bandit, and so Bobby would have come from the computer science side, where pretty much anything can be solved as an upper confidence bounding policy. So I'll look into his work. I haven't seen that particular piece of work. But now you have the weather problem that puts it in this world that the bandit people like to call contextual bandits. So you have the context of the weather. That means now you're trying to learn a decision in the context of the weather. Now, what the contextual bandit people do is sort of like, well, they want to learn a function that says, well, what's the right answer as a function of the weather? My guess is in your high-dimensional world, you're not going to actually do that. But I think it's an interesting vocabulary to bring into this problem.
Yep, no, that's a good point.
Mm-hmm. Everybody's gone.
And Carla, also, this is one of these areas where I love the intermingling of the more OR type tools and the more, CS reinforcement learning type of thinking.
Mm-hmm. Yeah. And actually, more and more, we see this between learning and optimization.
Yep.
In fact, last week, Zico gave a talk about, really removing those barriers or, fusing them. So very good. Oh, that's Zico.
I came back to my computer. I had to sit up for a second, but I came back and I realized that I hadn't turned my video back on yet.
And we were bad-mouthing you. Yeah. So we were talking also about how you are bringing together this, learning and optimization, and so fusing things.
Yeah, I mean, I think that there's ways to sort of learn in the context of the optimization objective, but of course, this is the scale of the problems the optimization problems that he's solving is much larger than what we were talking about. So there'd be plenty of interesting work to be done.
Other questions?
Well, of course, I guess, but I think you alluded to that. that you don't have zero flexibility in terms of incentives.
Yes, yeah. They're working. So so there was this interesting program that they put in place over the summer where they effectively had 1% of their user base that could enter in a competition every 2 weeks for earning badges for the most number of good rides, and then ran a lottery in the style of logic work. And this actually, it started actually with real prizes. In the end, it's still real that it's a really good deal for them, is that they just did 1 week extension of their annual subscription, which is really an effective way of just changing the price. This is really, putting in pricing, at least in an expectation sense, of people doing good rides. Because there are a lot of rides that you just would love for people to happen.
Then you do have some.
So they did it in a limited way, but we've now been working to sort of figure out a dynamic incentive system that they're going to put in place for the coming season.
And scalable.
Yeah, and that it'll be available to all users.
That's very interesting.
So and then we'll see how much an effect that has.
Okay, everybody, I think we've come to the end. Thank you so much, David. This was a great talk, and we will reconvene in the coming weeks. See the schedule.
Very good.
you.
Thank you.
Thanks again.